My name is Reyhaneh from Seoul National University. I'm glad to introduce our paper, which has been published in WECV 2024. The title of our paper is ICF-SRSR Invertible Scale-Conditional Function for Self-Supervised Real-World Single-Image Super-Resolution. Single-image super-resolution as a fundamental vision problem is a procedure to reconstruct a super-resolution image from a single low-resolution image. The recent denoising methods usually resort to supervised learning on the large-scale synthetic dataset, which prevents their real-world applications due to the domain gap. To reduce biases from synthetic training data, zero-shot methods and fully blind SR approaches have been proposed. However, they either rely on a non-degradation assumption or explicitly utilize the image distribution. On the other hand, a class of methods interpret SR tasks as a domain transfer problem between LR and HR distributions. These methods are biased toward handcrafted downsampling functions or need paired or unpaired data. We believe that self-supervised learning is an alternative solution to mitigate the mentioned limitations for the real-world images. Therefore, we propose a novel invertible scale conditional function and utilize it to design our self-supervised SR framework without requiring paired or unpaired training data, a specific downsampling operator, or adversarial loss. In this paper, we define an invertible scale-conditional function, which is a specific resizing function and acts as an operation and the inverse operation for different scale conditions. Based on the concept of ICF, we design a self-supervised SR framework. With different scale conditions, our method can simultaneously super-resolve and downsample a given LR image. Then, by repeatedly applying our model, we acquire two outputs. For an ideal ICF, both outputs should be the same as the original input image. Accordingly, with only the input image as the supervision and without requiring any paired or unpaired LRHR training samples, our method can learn up-down and down-up operations simultaneously. Learning these two operations simultaneously leads in learning feasible upsampling and downsampling operations. In other words, in the up-down stage, the network can learn to downsample the generated SR image by restoring the output as the approximation of the original input. On the other hand, in the down-up stage, the network can learn to upsample the generated LLR image. Therefore, by leveraging the learned upsampler and downsampler, we can generate favorable SR and LLR images by employing the learned model on the input image with the scale conditions S and the inverse S respectively. To train the proposed model, we design a set of self-supervised loss functions. First, we formulate the consistency loss, which preserves information during the simultaneous up-down and down-up stages. Furthermore, to stabilize the training and preserve colors between the input and intermediate images, we utilize color loss between the downsampled images. We train our self-supervised method on the LR images from the real-world RealSR and DRealSR datasets and compare the results with the various supervised and unsupervised methods trained on real and synthetic datasets. We illustrate that our self-supervised method can achieve superior performance compared to the methods pre-trained on the synthetic datasets and also the existing unsupervised method. We also qualitatively compare the super-resolution results and their corresponding error maps with respect to the GT for an image captured by each Nikon and Canon camera. We demonstrate that our self-supervised method can achieve comparable and sometimes better performance to the existing supervised method, which is trained on real paired images. We train and test our method on a single noisy image, and the result shows that our approach does not require a large-scale training dataset to outperform the other methods. More experimental results are available in the paper. In conclusion, we propose a novel invertible scale-conditional function and utilize it to design our self-supervised SR framework, which can simultaneously super-resolve and downsample a given LR image with different scale conditions without requiring any paired or unpaired LR-HR training samples. Experiments show superiority of our self-supervised method on real-world datasets compared to supervised methods trained on the synthetic datasets. Thank you very much for listening. Our code and the pre-trained models are available at GitHub.